Hello everyone, this is Professor Iris Miano with the Day 13 lecture in Math 50 Pre-Statistics. We're going to cover sections 3.3 and 3.4. 3.3 covers dot plots, stem plots, and time series plots, while section 3.4 covers histograms. We've got some new terminology to define, so let's go ahead and hit the ground running with the definitions of discrete versus continuous variables. And these are two different kinds of quantitative variables, just to be clear, as opposed to qualitative variables, which were introduced in the last lecture. So these two kinds of quantitative variables, a discrete variable is a variable that has gaps between successive possible values. Let me write that down for you. Oops, let's add some notes. And we'll go purple with it. A variable that has gaps between successive possible values. Whereas a continuous variable is defined as a variable that can take on any value between two possible values. Okay, in order to further solidify the difference between discrete and continuous quantitative variables, let's entertain a few examples. So at these 4 examples, we're going to identify whether the variable is discrete or continuous. Number 1, the number of dogs a person has. Well, one way that you can tell if it's discrete or continuous, like a general rule of thumb is like, well, can you have a fraction of that thing? And if that's not the case, then chances are you have something that's discrete. And in fact, that is definitely what's happening here. Okay, it's the number of dogs that you can have is discrete. Okay, you can't have 5.7 dogs. It doesn't make any sense to think about it that way. Okay. However, the speed in miles per hour of an airplane certainly is the speed of any object could take on a value that involves a decimal or a half or something like that. You can go 15.7 miles per hour. If you're talking about an airplane, then we're talking about hundreds of miles per hour. But it could be 752.87, right, miles per hour. That's perfectly fine. So we would say that speed in general is a continuous variable. The weight in ounces of 14-inch cheese pizza. Well, it doesn't need to be a cheese pizza, but just to give you a visual there, the weight of anything is continuous. Because you could certainly have fractions of pounds going on, or ounces, or whatever the measurement scale is. The number of strings on a musical instrument, certainly in order to pluck a string on a musical instrument, you cannot use a fraction of a string, right? You have to have a whole string. So that would be an example of a discrete variable. So hopefully that makes sense. Yeah, in general, I would stick with being able to determine if something can be represented by a whole thing versus a fraction or a decimal of a thing, and then that usually is key elements involved in being able to distinguish between discrete versus continuous. Okay, so we're going to take a sharp right turn here and describe the definition of a percentile. Okay, so the kth percentile of some data is a value that is greater than or equal to approximately k% of the observations and is less than approximately 100 minus k percentage of the observations. So let me go ahead and break that up into 2 pieces here. Is greater than or equal to k% of the data observations. And it's less than or equal to, or excuse me, oh no, it's greater than or equal to, so it's less than, sorry. I'll make sure I get the definition straight. Let me rewrite, I got a little messy with that one. Let me check my handwriting a little bit. Less than the 100 minus k% of the data, the observations. Okay. Now there's a particular percentile that is used quite a bit, and that is going to be the 50th percentile. Okay, so the 50th percentile is greater than or equal to, right? To 50% of the data, according to, you know, the generic kth percentile definition of observations. Also simultaneously, you know, it's less than the other 50%. So it is known as a measure of center for the distribution. Of observations. And furthermore, something that we'll get into a little bit later on, it's also further identified as the median. Okay. We'll define that a little bit later on. Just for now, just put the word median and that'll be good enough for our purposes. All right. Now, we're going to explore 3 different ways to present data with a visual, like a figure, okay? And the first one that we're going to dive into is dot plots. Now, dot plots are a way for us to get a quick visual representation of data in such a way that we could see the spread very easily, and you could see if any values are have a high amount of repeats in the data set, whereas if you're just scanning the numbers, you might not necessarily be able to see that very clearly. So it's just, let's see, it's just another way to take in all the information. So it's a visual way to take in the observations which easily shows spread and frequencies of observation. So I'll just say frequencies. Leave it at that. Okay, so below we have a table of students scored for an applied calculus class for test 1. Okay, so notice that there were a few students that got 100%. Wow, they on top of it and studied super hard. Maybe, maybe not. And those are highlighted in red. And then there's a 38 score that's in blue right here. So I imagine that that's going to be the lowest score, I would assume. Okay, and then notice that all of these scores got put on and spread out on a dot plot. So the way that you will create a dot plot is you will have basically a number line with 1 tick mark per unit. You need to have a tick mark for each individual possible score that you have there. So here's the horizontal labels points, the title is the scores on test 1. And then, but the tick marks are only labeled by 5s. So could you imagine if you labeled every single tick mark all the way from 35 to 100? Yikes, that'd be crazy. And you need to determine by noting what is the smallest possible value in the data set, you needed to find a good end place for, the number line. And of course, it goes all the way up to 100 because a few students did indeed super ace that exam. Okay, so we have an idea of how we need to create this number line for this particular data set, hopefully. And notice that each dot represents an individual score. So there was, as you could see with the 85, right? There were 4 dots on that particular score, so 4 students ended up getting that score, and that was the most common score that they had, which is also called the mode, but we'll define that a little bit later on. So anyway, let's go ahead and answer the questions that we see here in regard to these test scores. It says each student who scored at least 90 points received a grade of A. What proportion of the students earned an A on the test? Okay, so at least 90 received an A. So if we're talking about including 90, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 13 students, right? Out of how many students did we have total? Did it say? Well, we have 1, 2, 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 30 plus these 5. It's 35 students total. So you see how I was able to determine how many total students there were without actually having to counting every single one of them? How tedious would that be? So in order for us to determine this, so this will work well enough for a proportion. If we want our proportion to be in the form of a decimal, we could reach for our calculators and take 13 and divide it by 25 or 35, excuse me, and we'll get about 0.37. So the proportion of students that received an A grade was about, and I'm putting the word about because I am rounding this decimal to the nearest hundredth, so maybe I'll even put a little squiggle equals there, 0.37. Okay. Find the percentile of the test score 70 points. Okay, so 70 points is what right here? Okay, and so we want to see how many students are beneath 70, and that'll determine, that'll be able to help us determine what percentile it is. So that'll be 1, 2, 3, 4, 5, 6, 7. There's 7 below, right, out of 35. So, but this will be the 8th out of 35. Okay, hold on just a moment. Got a call coming in. Okay, sorry about that, we're back. So, sorry, we are miscounted here because we have to take how many are less than or equal to for a particular percentile here in order to find the value of the percentile. So that's 1, 2, 3, 4, 5, 6, 7, and include the 70% there, or the 70 score. So that'll be 8 over 35. My apologies, I misspoke earlier. So if we are going to type that into our calculator and get a decimal approximation, again, round to the nearest hundredth, we'll get 0.23. So that means that the score of 70 is in the 23rd percentile. I was about to make an error there, so I'm so glad I was able to catch that for you in the midst of making this video. If you want to find the percentile, it's probably easiest to count how many observations are below it and then include that number as well, and then divide by the total number of observations. And the percentage that you get there is the percentile. All right, now let's find the 50th percentile. Now that'll happen where we have So if we have 35 scores, then you'll want to take half of 35, which is about 18, right? If you were to cut 35 in half, 35 divided by 2 is 17.5. Because the 50th percentile is supposed to be like halfway through the data, right? And if you have an odd number that you're trying to cut in half, you're going to get a 0.5 out of there, but just round that up to the next whole value, okay? So we count the dots from left to right, we'll reach the 18th dot, which is at 85 points, right? Okay. So, and again, if you count from left to right, so from left it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is the 18th dot, right? If you're counting from left to right. Now, if you're counting from right to left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It might be this one. In any event, you're still in score 85, thank goodness. So there's no doubt on which point value you're on. So the 50th percentile score is 85. All right, and that's that. Cool. So let me know if you have any questions about dot plots based on that particular example. The next visual representation we're going to explore for data is called a stem plot, or a stem and leaf plot. And it breaks the data up into two parts. The leaf, which is the rightmost digit, or the ones place digit, and the stem, which is going to be the other digits. Okay. Now we're going to use the same data, the scores on test 1 for the pre-calculus class, or whatever it was, and we're going to go ahead and use a stem plot in order to represent it. So what's good about stem plots is that you can look at scores based on, what's the word I'm looking for? Or scores. You could look at data based on clusters by tens, basically. So the idea is that it's a visual representation of data clustered by tens. Which lends itself really nicely to exam scores because the letter grades are clustered by tens. If you're, in the 80s, you got a B. If you're in the 70s, you got a C, and so on and so forth, right? So the way that we will organize our data is to basically make a little chart. Okay? So we'll have the stem, which is going to be the tens, and the leaves. Okay? And so which stem are we going for here? Well, our smallest stem is the 30s, so that'll be a 3 in the tens place. And then we go up 4, 5, 6, 7, 8, 9, and so on and so forth. Okay, so what we can do is either we can create one stem and leaf plot where we order the leaves in order from smallest to largest as we go, or we could just put them all down in a stem and leaf plot and then reorder them later. I think it's kind of nice just to organize them as we go. So you're basically going to scan the entire data set for any scores that are in the 30s, and then mark them off as you go. So I'm seeing here that I have a 38 right there, so that'll be a stem and leaf of 38. Well, I guess before we put it down, we want to see if there's any other 30s in here. So do we see any other 30s? We do not. So 38 is going to be the only The 8 is going to be the only leaf on the 30 stem, okay? Now, 40 stem. Are there any scores that are in the 40s? So scanning, scanning. Do you see any numbers that have a 4 in the tens place? I don't, so we get to skip the 4. Okay. So, 5. Any scores in the 50s? I'm looking offhandedly, and I do not see any, so we'll skip the 5 as well. 6. There are definitely scores in the 60s. There is the lowest possible score in the 60s, which is a 60. So I'll put a 0 right here for that score of 60. Do I see any others? Well, I have a 62 right here, and a 65, another 65, and a 68. So we want to do those in order, 62 being the smallest. There's 2 65s, so we'll put a 5 and a 5, and then a 68. 8. Okay, moving on. 70s. Let's see, let's scan them out. We've got 73, 75, another 75, a 78, a 70. So that's the smallest possible one, so we'll just go ahead and put that one in. And then that's it. So, okay, now starting over, 70s in there. Was there a 72? There was not, but there's a 73 right here. And then there were no 74s, but there were 2 75s, right? 2 of them. So that's a 5 and a 5, and then a 78 as well. Boom, 78. Okay, now 80s. Goodness, there's a lot of those. I see 180 right off the bat. Oh, look, I've missed a 68. Did you guys see that? So there's another 8 right here. Whew. Good thing I caught that. All right, now going back to the 80s stem. There's an 80 right here. There's an 83, but is there an 82? Oh, there's another 80. Boop. And any more 80s? Are there any 81s? Looks like no 81s. 82 looks also like a no. How about 83? There we go, 83. Any other 83s? No, but there's some 85s here. No 84s. 85, 1, 2, 3, and 4. 1, 2, 3, 4. 1, 2, 3, 4. 88, sure, there's 3 of those, but there's no 86s and 87s, right? Let's just double check. Nope, we're good on that. So 88s, there's 1, 2, 3. 1, 2, 3. Is there any 89s? Let's see, 89, 89. No 89s, just 90s and 100s left. Oh, look at that. I forgot to put the last stem. There's supposed to be a 10 there because there are scores of 100. So what's going on with the 90s? Is there a 90 in here? Yes, I see one right there. So I'm going to put a 0 down there. Any other 90s? Right there. Another 90. And then it looks like the next value up from 90, there's no more 90s, so there's 93s. 1, 2, 3. 3 93s. 1, 2, 3. And then 3 93s as well. 1, 2, 3. Or 95s rather. Sorry, I think I said 93. I meant to say 95. There's 3 95s. There's 1, 2 98s. Okay. And then it looks like there's 1, 2, 3 100s. All right. So there you have it, folks. That's a stem and leaf plot. And it just takes a little bit of careful observation while you're doing this to be able to make the stem and leaf plot in its final form from the beginning. You just need to be considering all possible values in a particular stem from smallest to largest to make sure you get all of them for a particular score before you move on to the next higher score. Okay, so there you go. There's a stem and leaf plot for that data set in its entirety and in its final form. If you want to just put the values down as you see them reading from left to right, like in this table of scores, you will need to make the stem and leaf plot again such that the scores are in order from left to right in ascending order. Okay, cool. Now let's look at some time series plots. So time series plots, the idea behind those, like what's good about them, is when you have two variables that you want to compare and one of them is time. So this allows a variable to be considered against time. So if you see changes as time progresses in your data, then you want to create a time series plot. And here is such an example: years versus number of stores. So you'll notice that there's no background information. Oh wait, there is. This is a time series plot and the numbers of Radio Shack stores shown below. Yeah, Radio Shack is dying, probably because of Amazon. Anyway, there's just not as many stores anymore because, well, there's Amazon and also most of the things that you get for like your most important technological bit of machinery, your phone, you would just get from like the store where you bought the phone, like the carrier. In any event, we don't need to talk about the reason for the decline, but we're definitely seeing a decline in the number of stores over time. So we can use this chart in order to make some estimates, and that's what a lot of these exercises subsequently are going for here. So it wants us to estimate the number of stores in 2004, okay? So that'll be 6,500 stores, I would say would be a good estimate there. And be in 2010, which is going to be somewhere halfway, maybe a little less than halfway between 6,000 and 550. So maybe like 570, or sorry, 5,700 rather. Sorry, I really intensely misspoke on that number. 5,700 is what I would say would be a good estimate for that particular value. So let me just go ahead and answer this. The approximate number of stores in 2004 and 2010 was 6,500 and 5,700 respectively. So respectively is just a word you use in order to say that the order in which you're listing things in the describer is associated with the order in which the the main things were presented. Okay, now let's estimate when there were 6,000 stores. Okay, so now we're on the vertical axis. When was there 6,000 stores? That was 2006. And when there was 7,250 stores. 7,250 stores. Well, that's probably about, 2002. So there were about 6,000 and 7,250 stores in 2006 and 2002 respectively. Has the number of stores increased, stayed approximately constant, or decreased, or none of these from 2002 to 2013? Definitely the number of stores have decreased. Like, that couldn't be more obvious, I think. The number of stores has decreased over 2002 to 2013. A student estimates that there were 5,100 stores in 2013 and that the number of stores had been decreasing by about 200 stores per year. He concludes that there were 5,100 minus 249, 4,900 stores in 2014. What would you tell that student? I would tell that student to be careful making predictions based on data, just in general. This is something that we want to be careful with, because we don't want to assume that the trend is necessarily going to follow what the data is doing, or like if it's going to continue decreasing, or how much it's going to continue to decrease by. So I would tell the student to be careful anytime they feel compelled to make predictions based on data. Predictions the trend cannot be assumed. You're going to see this idea repeated again and again. Okay, statistics is great, and it can help us, you know, try and do lots of stuff with making decisions, but you'll still want to be careful with it. That's what is mainly the crux of it. Okay, so that is an overview of those three types of data representations associated with quantitative data. Okay, let's move gears over to section 3.4, where we're going to talk about histograms, which are basically bar graphs. Oops, let's get our add notes going on. Bar graphs, which we've already kind of dipped into a little bit, but what is special about them? Well, you can have frequency histograms, or you could have relative frequency histograms. You can have density histograms, which are basically relative frequency ones, just a little bit of a different spice to it. But it's basically just a bar graph with a little bit of a difference on the horizontal axis. So you're going to have classes instead of categories. Classes instead of categories on the horizontal axis. Okay, so let's look at this scores, table of scores. This looks pretty familiar, doesn't it? So some different scores are highlighted in blue, so we'll see what that's about. Let's create a relative frequency table and a relative frequency histogram here. So first, let's go for frequency. Okay, oh geez, hold on, I'm getting another call. Just a sec, guys. Okay, back to it. Sorry for that interruption. So one thing we could actually use here is some of the information from the stem and leaf plot. So I'm not going to go back to that document you could reference it again if you have it available to you readily. Ultimately, what we want to do is come up with the frequency and then the relative frequency. So I'm just going to put freak and then relative freak. Not like your freak of nature, like you're short for frequency. Okay, and we need classes here. So what are the classes? Well, you need to split up the data into, equally sized chunks such that the classes do not overlap. So that can be a little bit tricky. So the first frequency class I'm going to put is 30 to 39, scores 30 through 39. So that's going to be all your 30s, 40 through 49. Notice that I'm not going 30 to 40, 40 to 50, because then we're going to have an overlap where 40 is in one class and then also another class. So you have to break it up this way for it to make sense. So 59, 60 to 69. You'll notice that some of these classes are going to be empty. That's okay. 80 to 89, 90 to 99, and this last one is going to be super weird because you have to have a class for all this 100 scores, and it's going to be technically to 109, even though that's like it's not possible to get anything over 100. So those are our classes, and the frequency is just going to be right here. So there was one instance of 38, score 38, so that's in this class. We have 0 instances here, here, and then for the 60s, we have 6 instances there. 70s, there were 5 of them. There were 10 Bs, 10 As, and then 3 super As. Okay, and now remember, there were 35 scores altogether, so the relative frequencies are going to be 1 over 35 for this one, which is approximately, and 3 decimal places is good for this, 0.029. These are all 0, right? 6 out of 35, and we'll get approximately 0.171. 5 out of 35, that's also 1/7, which is 0.143. 10 out of 35, which is about 0.286. Again, 10 out of 35, same approximation there. And then 3 out of 35 is 0.086. 0.086. Okay, so now that we have our relative frequencies, we could put this in make a histogram of it, okay? So we need to look at how many classes we have. 1, 2, 3, 4, 5, 6, 7, 8. So we want to look at the horizontal width of the grid that we need to work with. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Cool, so I think we can go every 2, right? And that's going to be the width of our each class. So this is going to start at 30 and go to 40, right? 50, 60, 70, 80, 90, 100. And technically that'll be 110. Okay, so the bar that I'm going to draw for this histogram, it's going to be 2, two blocks wide. And so the implication here is that this bar that I'm going to make it, 0.29, I need to do my vertical tick marks as well, but whatever the height is, it's going to represent from 30 to 39, so it'll be just shy of this 40 is the implication, and then whatever height is appropriate for this next bar, it'll be from 40 to 49 class, if that makes sense. So this is supposed to be the class. Let me go ahead and label that. Okay, so cool, 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 cool. What's the highest relative frequency that we have? It's 0.286, right? So maybe we'll go, since it's 1, 2, 3, 4, 5, 6, 7, maybe every 2 it'll be a tenth. So here's 0.1, 0.2, 0.3. I think that'll be fine. And this is the relative frequency. Let's see. Sure. Okay, so let's go ahead and pick a different color just so we can have a nice contrast to what's going on here. And yeah, let's go ahead and do up this histogram. So we're going to make a bars. So it's basically a bar graph, but we just have these classes on the bottom instead of any kind of category. Whereas when we did bar graphs earlier, it was just the horizontal label with some kind of more qualitative category label naming. Okay, so let's go up to 0.029. So there's 0.1. Here's 0.05, so 0.29 is going to be having a height, a little bit more than half for this first block. Okay, and fill that in. Great. So from 40 to 49, there's 0. From 50 to 59, there's 0. From 60 to 69, there's 0.171. Okay, so here's 0.1, here's 0.15, 71, something like that. All right, cool. Beautiful. 70 to 79, that's 143, so that's going to be a little bit less, right, than 15. Be appropriate there for that height. Cool. 80 to 89, we get 0.286, and we're going to get that same value for 90 to 99 as well. 286, we're going to be somewhere right around here-ish. Yep, we could go for these bars and these bars. Just color them in as much as you care to. Not gonna get too crazy with it. All right, and then from 100 to 109, technically, although there's just scores of 100 in here, there's 3 of them. That's 0.086. So that's going to be a little bit less than 1. Cool. Then there you have it. Histogram done. Let me know what you think about that. All right, area of a density histogram. So basically this relative frequency histogram is the same as a density histogram. It's just generally understood that the heights of each bar is going to be the relative area. So let me go ahead and write some of this stuff down for you. Heights of bars are area of the bar representing each class. So think relative frequency. Just put relative for short, and also the sum of the height of all bars has to equal 1. Okay. Cool. Let's talk about modalities, okay? So if your distribution is unimodal, then that means it has basically one mound that it follows. I'll definitely draw some quick pics of each of those Okay. If there is one mound. It's bimodal if it has two mounds. And it's multimodal if it has more than two mounds. So here is a unimodal, right? Here's your distribution, and it looks like that, right? One mound. Bimodal is something more like this, right? Two mounds. Multimodal is something, right? Something like that. Cool. Sorry, that needs to be associated with bimodal. Meant to do there. Okay, so just some quick picks about like what the distributions look like when they're plotted, and of course you might have bars underneath these curves, but these curves are generally representing the data, like if you're just kind of taking a faraway look at it. Okay, so unimodal, if a distribution is unimodal, it can have three different kind of modes to it, and by modes I mean looks to it. So what I drew as my generic unimodal, unimodal, excuse me, that's the correct word, was actually a symmetric looking one. So by definition, just a moment, make sure I get the wording that I want here. Left tail of the distribution is roughly a mirror image of the right tail. So you need to know about tails in order to know what skewed left, skewed right means. So anyway, let me define skewed left first. The left tail is, if the left tail is longer, don't worry, I'm going to draw pictures for you. Then it's skewed left. Skewed right if the right tail is longer. And then symmetric if the tails are about the same size, approximately equal on both sides. Okay, so here is a unimodal that is skewed left. So it has a tail and then right, a hump. Here's what it looks like if it's skewed right. So you have your hump and then a long tail on the right side. So this is skewed left, skewed right. And then symmetric is like this. Right, where it's like a good, symmetric. The left and the right tails are about equal. Okay, cool. Now let's entertain a couple of specific examples where we're saying a frequency histogram here for this particular example. Let me read it to you in its entirety. The Gallup organization classifies Americans as very religious if they say religion is an important part of their daily lives and that they attend religious services every week for almost every week. In 2013, 175,000 American adults were surveyed about whether they are very religious. A histogram of the percentages of those surveyed who are very religious is shown in the figure. A little bit of a typo there. You guys see that? Shown in the figure. Okay, so here's the figure. We have percentages in the classes. So just to be clear, this is 20 to 24% right here is this class. This is 25 to 30 or to 29%. This is 30 to 34%, and so on and so forth. We have to cut it off just at the, the check marker at the beginning of the next class. And the frequencies are given to us. So this means we can read this as 2 states reported that they were between 20 to 24% very religious, like 20 to 24% of the state's respondents said that they were very religious for 2 of the 50 states, okay? So yeah, we're assuming that all 50 states were participating here. So if you were to, add up all of these frequencies, it should add up to 50, right? Okay, what would you describe as the shape of the distribution? I would say that it is unimodal and symmetric. So the first thing you want to report for this is telling us what kind of mode you think it has, what kind of modal representation. If it's unimodal, bimodal, or multimodal. And if it's unimodal, you have to further specify if you think it's symmetric, right skewed, or left skewed. So that's what we've done here. It's unimodal and symmetric. It's got one mound, and both of the tails are about the same size, I would say. And then next, we want to estimate the number of states that were at least 50% of those surveyed are very religious. Number of states were at least 50%, at least 50%. So at least 50%, so that means 50% or more. So that would be, there's a frequency of 4 here, then 2 more, then 2 more. So it seems like 8 states, right? Sorry, so let me just be more specific. At least 50% means that 50% is the least, and we need to go upwards from there. So we need to take these 4 states, these 2 states, and these 2 other states, add them all up, and that's how we'll get 8 states. There are 8 states that report at least 50% religious. Okay. Mississippi and Utah have the highest percentage of those surveyed who say they are very religious. Estimate the percentage of each of those 2 states. Okay. Well, if they're the highest percentages, they're going to be in this class right here. So this is Mississippi and Utah are the 2 states that are in that class. Oh, I'm totally not spelling Mississippi correct, and I should be able to. We all got brainwashed with the Mississippi. This is Mississippi and Utah right here. So what is the percentage range in that class? So we'll say Mississippi and Utah are between 60 and 64% religious. I cannot spell to save my life. Here, let me try that again. Religious. Okay, cool. One more question for this type. It says, identify the class that contains the 50th percentile, which is a measure of the center. Are the observations in this class typical values? Explain. Okay, let's see. 50th percentile, huh? So that's going to be exactly halfway. So there are 50 observations, one for each state. So we should look for the 25th observation. And starting from the left is conventional here. So if we go from 20 to 25%, that's 2, right? Observations there. 2 more is 4 total. And then plus these 8, that'll be 12 so far. So the first 12 states are right here. And then we're going to add 10 more, which is 22. And then adding 10 more will be 32. But somewhere in this class, this percentage class, we have the 25th observation lies in there. And that's the halfway observation. Okay, so that means that the 40 to 44% class has the 50th percentile. The 40 to 44% class contains the 50th percentile. Then it asks, are the observations in the class typical values? Explain. Now here's what you want to say about this, okay? How many observations are in this 50th percentile class? Well, there's 10 observations, right? There's 10 of them in here. So 10 observations out of 50, that's, 1 out of 5, that's 20% of all of the observations are in that particular class. So if 20% of the data is there, would you say that that's typical values? Well, I wouldn't, actually, because, if it was maybe like half of the data was in that one particular age class, then I would say, oh yeah, that would be more edging towards typical values. Or if there was like 70% of the data, well, that would be very compelling to be able to say that that was a typical value coming from that particular class if 70% of the data lived in that class, but only 20% of the data lives in that class. So I'm going to go ahead and state that as my reasoning for saying that it's not typical. Only 20% of the data lives in that class. So it is not typical. Okay, so that's something we can touch on a little bit more if you like in class. Just let me know. But for the time being, let's go ahead and swing on over to our last example of this lecture. And we are going to look at a density, which can also be thought of as a relative frequency histogram. And it involves average response time to fix potholes. So here's the example. I'll read it in its entirety, the prompt anyway. The average number of days it took Chicago's Department of Streets and Sanitation to respond to requests to fix potholes are described by the density histogram for each of the weeks in 2012 and 2013. Okay, so let's go to number 1 and identify the class that contains the 50th percentile. Are the observations in the class typical values? Explain. Okay, so here we go. We'll do that typical values kind of a designation again. So let's see. Where does the 50th percentile live? Well, 34% of the data is in this very first class, okay? The first week, basically. And then the next 33% after that, so it's like there's like a third of the data, and here's like the next third of the data. So what we want to glean from this, just a moment, is that 2/3 of the data is going to be in the first 2 weeks of the data collection effort. Like, so it takes 2 weeks or less, basically, is like what happens 67% of the time, okay? Furthermore, the 50th percentile is going to be in the second class because we're 34% of the way just going from here to here, and then all you need is another, 16% tacked on top. That's definitely going to be in this age class, is the 50th percentile, without a doubt. Okay, so the 50th percentile exists in the 7 to 13 day class. Okay, and yes, I would say that it's typical because it itself contains a third of the data, and that's like a lot more than all of the other age classes are far smaller. except for like this first one. So we would say, yeah, a pretty large chunk. So yes, it's typical. Because a third of the data lives there. And all the other age classes, or all the other classes, excuse me, are much smaller, with one exception, the first class, of course. With one exception. Oh, Lord. Okay. A little bit sloppy, and I trailed off a bit there, but hopefully you guys get the drift. I'm going to go ahead and switch up the color just for funsies. And also, I don't want this bleed over of my answer to get confused on what I'm going to put for number 2, which states, for what proportion of the weeks was the average response time at least 42 days? At least 42 days, so that's here onward, okay? And notice that none of these bars have values associated with them because the bars are too small, and I guess the convention was started that the values need to be placed inside. But one thing we can do is recognize that since this is a density histogram, we know that the area underneath these bars has to add up to 1, and we're given all the areas here, right? So if we add up these areas, add them all up, you're going to get, if I'm not mistaken, 0.97 is going to be the sum of the areas of all of the bars below 42 days. So I'll note this. All the bars summed below 42 days, excuse me, is 0.97. So the average response time at least 42 days proportion is 0.03. If we're talking percentages, it'd be 3% of the time. You got to wait longer than 42 days. 42 days or longer, I guess is what I would say. Okay, last question, and then I'll turn you loose on this lecture video. From inspecting the histogram, a student concludes that in 2015, the average response time will be less than 21 days for 79% of the weeks. What would you tell that student? Again, it seems like the student might be making predictions based on this data set, which could be very specific to this particular location or situation. So trying to make, or time frame. I don't know. There's just lots of variables going on here. So trying to use this data set to make predictions is assuming the trend continues. So I would say the student should understand that the trend might not continue. So making predictions off of data can be dangerous. Off of data can be dangerous. Okay, folks, that's it for today. Let's go ahead and have a lively discussion when I see you in class again. Have a great day.